Welcome to the One Source PH. Our topic in this video is all about the conservation of energy. Actually, this is a law that states that energy is not created nor destroyed. But first and foremost, before we go and try to tackle this lesson, we should first define some basic terminologies and concepts that will help us to understand better the law of conservation of energy. So let us define energy. So energy is defined as the ability to do work. Then let us define what is work. Work is actually a product of force and the distance or the displacement that is traveled by the object that is being moved. There are types of force in this universe, and basically they fall into two categories. So the first category is the conservative type of force, wherein the amount of work done is independent of the path taken by the object, and it only depends upon the final and initial position of the object. So I can give you an example about this by trying to consider in moving a ball in a gravitational field, which is free of friction and free of atmospheric drag, all right, or air drag. All right, so let's draw a ball somewhere right here. So I have a ball which is in position 1, and I want to move this ball in some position right here, which I call position 2 or point P2. So you can actually move the ball and take some path. All right, so you can take this path, long path, and go here. So this is the first path. We call this path 1. Then there's another one which is a bit longer or a bit shorter. So this is path number 2. Alright, so technically you're trying to move the ball, so you are spending energy and you are doing work. Alright, but it doesn't matter because only the initial and final position matters the most. That is the displacement, which is a straight path, okay, shortest path, okay, from point 1 to P2. So this is what you call the displacement. And this rule claims that the amount of work done when you choose point or path 1 or P1 or say path 1, amount of work using path 1 is equivalent to the amount of work done or spent by taking path number 2, and this is just equivalent to the amount of work when taking the shortest path or the displacement. Alright, so work in path number 1 is equivalent to work in path number 2, which is also equivalent to the work done when taking the shortest path possible. Alright, so that is what we mean by independent of the path. It doesn't depend on the length of the path. So you should put in mind that friction and atmospheric drag or the dissipative force must not be present when you're trying to describe a conservative type of force. So if we have the conservative type of force, we also have the counterpart, which is the non-conservative. All right, these are forces that are dissipative, all right, such as friction and air resistance. These forces take the energy away from the system as the system progresses, energy that you can't actually get back. Okay, these forces are path dependent, therefore it matters where the object starts and stops. So I hope you have identified and you will be able to differentiate which is which among the conservative and non-conservative type of forces that are present in this universe. Alright, so we have forms of energy, but technically, generally, they fall into two categories. One is the potential energy, and the other one is the kinetic energy. Under potential energy, it has its subtypes, which is very familiar to us. One is the gravitational potential energy. The other is elastic potential energy. So this energy is from or is derived from the elastic ability of matter. All right, by Hooke's law, it's defined by that. I think I have made a video for that, and I'll be making one in this channel also. All right, so next is chemical potential energy, which is stored in bonds. Right, so you can release this potential energy when you break or create chemical bonds. Electrical potential energy from charges. All right, so just like what powers the lightning. All right, so there is potential difference that develop between the ground and the clouds. So that energy is transformed into lightning. All right, so by a quick process which is happening to neutralize the charge. All right, so we have the nuclear potential energy. So there is something that is holding the nucleus of the atom together. We know that the nucleus has a lot of protons in it. All right, so these are charges that are trying to push other protons. All right, because they are repulsive. Because according to the law of charges, like charges will repel, and like charges will attract. And the repulsive force is given by the electrostatic force, actually, which is oh, that's not a good. So let's write the formula for the repulsive electrostatic force, Fe, which is equivalent to the product of the K, which is a constant, charge 1, charge 2, all over R squared. We know that the nucleus is pretty dense, meaning to say that they are closer together, so the radius of separation or the distance of separation is very small. So we can expect that the force of interaction is very large. All right, because the distance that separates them is very small, and the charges are yeah, so like that. And the question is, well, how does the nucleus stays together? Basically, there is a much stronger force that binds the protons together, and then we call that the nuclear binding energy. All right, nuclear binding energy. So this energy is released when atoms are split apart. Okay, fission and fusion. So that is a nuclear reaction. But we're going to talk about that in some other videos. For now, let's focus on the conservation of mechanical energy. That is the topic of this video. Guys, so if you like this kind of content, please give us a like and share this content among your classmates so that they can also learn how conservation of energy is happening. And you can also give us a comment or leave a comment down below if you think something is wrong or something is not right and you want to add something or you want to ask something. Put it in the comment section below, and don't forget to click the subscribe button and then hit the notification bell to get updated whenever I post new videos like this. I'm sure that this will help you to pass your quizzes or your recitations and have a better grade in the future. So guys, please, we need some support. Alright, so the next type is kinetic energy. So this is said to be the energy derived or vested to a certain object by the virtue of its motion. So one type is the thermal energy. So this is also known as the internal energy. So this is derived from the vibration of matter. So since it is vibrating, it has kinetic energy. So other type is the light energy, and actually light energy is, or light itself is a wave nature that carries energy. So it itself is an energy, and it also has a particle nature that gives its momentum and can actually knock away some electrons. So it can do work. So hence, it is a form of energy. And then we have the sound energy, which is derived from the vibration of air molecules. So they are vibrating, hence they have motion, and hence it is a form of kinetic energy. And then we have the mechanical energy, which is the topic for today. And later on, we're going to deal and explain more about mechanical energy. We have the electrical energy, which has two types. Actually, electrical energy and magnetic energy are working together to produce the electromagnetic yeah, energy. Okay. So we have two types. We have the AC, all right, or the alternating current, and we have the DC, which is the direct current. So this is from the oscillation of charges, oscillation, oops, oscillation of charges, and this one is from the potential difference. So this is one way travel of charges from high potential to low potential. All right, so later on maybe I can do some video about electricity, but right now, as I've said, let's focus on electrical energy, because the topic of energy is so well, wide and complex. Okay, so let's go ahead and try to talk about the nature's way of conserving and transforming energy. Actually, the major source of energy in our solar system is actually the sun. And we have the energy cycle that is present ever since the world began, all right, or ever since plants or the first bacteria that were able to do some photosynthesizing ability were born. But even way before that, there is a way on how the earth is trying to, or nature is trying to recycle and convert one form of energy to another. But that's not the topic right now. All we have to do is to understand that the sun is the main source of the energy, and this is used by plants, all right, which are called autotrophs, or the producers that make their own food. And plants and animals long ago ate these plants, and they became prey to the predator, and well, they die and they are buried down to the depths of the earth with intense heat and pressure. They are turned into what we call now as the fossil fuel. Actually, right now we still have this process because plants still do their photosynthesis. So we also get benefit from this process, and that's how we get our energy. Long ago, there are precursors of change in this planet, one of which is the blue-green algae called the spirulina, which have been here for around 2.5 billion years ago. Alright, so since then, spirulina plays a major important role in changing the atmosphere. So it's because of this species that we have a breathable and livable atmosphere right now. So it also has its health benefits. So this is the superfood that you need to take if you want to be smarter. All right. Yes. You can buy your supply of spirulina, and I'm gonna put the link or how to get this spirulina so that you can cleanse your body and have a super pellet. Okay? It will boost your energy to the max. All right. So since man is curious and we need energy to power our devices, man has also explored the way on how to conserve and transform one form of energy to others. So we have made machines. Man invented machines or devices that converts one form of energy to another. So pioneers of this move was way back the age of industrial revolution. We have Tesla, Okay, and we also have those who develop the steam engine. But a familiar example of this kind of device are the alternating current motor or the AC motor powered by AC current, and we also have the direct current or the DC motor, which is powered by DC DC type of electricity. All right. So next we also have the engine or the car engine, which is powered by fossil fuels or gasoline. And when it is burned and it explodes in the piston, it turns on and it tries to rotate the shaft, and that is connected to your wheels, and then you're moving. So there is a functional work that is being created by the combustion of fuel inside this engine. All right. So next, we also have developed something to fly. So we use turbine in order to fly, and actually this is it should be efficient because the fuel is so costly. All right. So we have, or man have developed the concept of harnessing the nuclear energy. So we have a nuclear power plant right here, and we have the core. So core is where the nuclear reaction takes place, and your coolant is getting heated, and this medium is the one that tries to push the turbine, all right, because it turns to superheated steam that can drive the turbine, which in turn drives the generator through the action of electromagnetism or electromagnetic induction will generate electricity, which is stepped up to several million volts then before getting transmitted into the pylons. We also have we are also using the step down transformer to bring it down to around 110 or 220 volts, which is the one we use to power our appliances. All right, so what's next? So we have conservation of chemical energy. So we extract or harness chemical energy coming from chemicals through chemical reaction. This process involves breaking and making of chemical bonds, and it means that chemicals transforms from one form to another, just like the reaction of fuel to oxygen that produces heat and some byproducts. Alright, so later on we will see that it is connected to the conservation of mass and energy, but let me give you a quick example of this chemical reaction. So let's say, for example, we have a hydrogen gas. Alright, so this is a familiar example in chemistry. Gases, guys, always occur in diatomically. Alright, so the plus sign says that they are reacting, and you have to we have oxygen species right here. All right, so you actually need to trigger the reaction, and once that is triggered, it will produce water. All right, let me just erase this. So it will produce water. Okay, let me just draw an arrow. All right, which will produce H2O. So right here, if you're going to count the before and after, you're gonna make some graph, so or table. So we have before and after. So you're gonna count the reactants and products. All right. So before, we only have 2 atoms of H2. All right. And 2 atoms H2 and 2 atoms oxygen or O2. All right, so here afterwards we only have so this is the equation, no? And we only have 2 atoms H2, so we don't have any problem with that, but we only have one atom, O2 or oxygen. So let's get that written. Let's write that, right? One atom O or oxygen. So there is an imbalance, okay? So for hydrogen, we don't have problem because before and after we still have two hydrogens. But right now we have a problem because we only have one atom of oxygen. So where did that go? And the reason is this is not a balanced equation, and we have to balance it to obey the law of conservation of mass and energy. So hence we're going to put some numerical coefficient before the reactants or before the product. So let's do that. So we need two oxygen. So we need to put two oxygen right here. So I'm gonna write 2 here. So we have 2 oxygens right now after balancing the equation. Yep. So this is the balancing part. All right. So we put 2 here. So the new count of products and reactants before and after is right here. We have 2 times 2. We have 4 H2. All right, and you multiply that there. So you have 2 O2. All right. So right now here we have 2 oxygen. All right, but here we only have 2 hydrogen. So we're going to put 2 here. So that's going to be 2 times 2. It's going to be 4 H2 and 2 O2. Yeah, 2 oxygen. All right. So that's it. That's how we balance the equation. We just put the coefficient right here so that the equation is balanced. So we have done that because we are trying to follow the law of conservation of mass, right? So which states that the mass of the reactants before and after the chemical reaction should be equal. All right, so this is actually the conservation of mass. All right, so it is and it must be it must go hand in hand with the conservation of chemical energy or of energy. So you should always put that in mind. And this is difficult to prove, and you need a lot of technical skills and complex apparatus in order to prove this, to measure that the amount of the reactant must be equal to the amount of the products after the reaction. All right. So if someone among you can prove that, I'll be happy, and you can actually comment down below if ever in the future, okay, you have been able to prove and have the ability. Okay, so go back and try to thank me by uploading a photo of you being able to actually validate the law of conservation of mass and energy. Alright, so we state that law as regardless of the form, the reactants and the products, the law of conservation of mass and energy must hold. That is, the amount of the product or the reactant must be equal to the amount of the products afterwards. Alright, so because there are many products of a chemical reaction. Sometimes it's gas, sometimes it's liquid, but you have to weigh them all. If you were able to weigh them all, this should be obeyed. Alright. So this is the mathematical interpretation of that particular law. And we state that the mass of the reactants is equivalent to the mass of the products. So conservation of heat energy. Hot objects like this which are the hot gases that is being burned inside the piston, can actually do work. All right, so the energy from heat is transformed into functional work, and you can do that by using yeah, this type of device known as an engine. All right, so basically we cannot convert 100% heat to 100% work. That means that we can only increase the efficiency but not 100% efficient. All right, such a thermodynamic system is not visible as of the moment. So because there is loss, we have friction, and yes, energy is dissipated. Okay, so we can only get high efficiency but not 100% efficiency. So if someone in the future were able to create a 100% efficient heat engine, guys, notify me, and I'll be glad to congratulate you for your noble deeds. All right. So comes next is the conservation of mechanical energy. So mechanical energy is conserved in a system if and only if the system is free of friction, all right, or of dissipative force such as friction and the atmospheric drag. If an amount of mechanical energy before the motion is equal to the amount of the energy or constant after the motion, hence we can say that the energy or the mechanical energy of the system is conserved. And I'm gonna give you an example of that using this. Alright, but actually you need something to push the cart upstairs, up the hill. Alright, so here it has a lot of potential energy, and once it starts rolling down, that potential energy is converted into some of it is converted into kinetic energy. All right, so there you go. There is a transformation of potential energy to kinetic energy. So next is yeah. So we'll try to create a formula or a mathematical expression for this scenario. That is to track down the changes in the potential energy before and after the process. So the potential energy and or plus the kinetic energy of the system before the process must be equal to the potential energy after, okay, and plus the kinetic energy after the process. So yep, so PE before plus KE before is equivalent to potential energy after plus KE after. So this this two, all right, is equivalent to the total energy of the system, or what you call the TE. All right, so if it doesn't change, it means that the amount or the total amount of the energy in the system is, or throughout the process is constant. All right, so put that in mind, because that is the other statement of the conservation of mechanical energy. That is, the total energy of the system before and after the process is constant. So we only change the form, okay, from potential to kinetic or kinetic to potential. Phases of conservation of mechanical energy, okay. So actually, even if an object is resting, it has its rest mass according to Albert Einstein, which he have proven using the E equals mc squared. So we're not gonna deal with Einstein's derivation of the E equals mc squared right now. No. So that will be reserved for other videos and other topics. So if you want that, please click the subscribe button, hit the notification bell, and get updated if and when I am able to release that kind of that video about Einstein and his derivation of the E equals mc squared. Alright, so let's go and move forward. by calculating the potential energy or defining the potential energy. So what is potential energy? Potential energy is an energy in matter or that is stored in an object due to its position. So relative to the source of force, okay, or of the conservative force, or yep, that is present. Just like if are going to place an object in a gravitational field free of friction and atmospheric drag, it will, or that object will gain potential energy. All right. So I have an example for you, which is I'm gonna draw right now. Alright, so say I have a building, so this is the ground, okay, and I have a building right here, which is 10 meters high, alright, so there's a height, h is equal to 10 meters high, and I have a box on top, alright, so that box has mass, and we say that it is 5 kilograms. Alright, and that 5 kilogram is actually affected or being attracted to the center of the earth through the force of gravity. So let's just assume that this is 10 meters per second squared. So that is the value of G. So assuming for simplification, to simplify our calculation. Alright, so we go back to our definition of work, which is or energy rather, which is the ability to do work. Hence, if we can measure work, we have also measured the amount of energy that causes the work to be done. All right. So let's just click the pen. Alright, so work now is given the formula earlier, which is equivalent to the amount of force times the displacement. So later we will know how to calculate this. Alright, so this force must be parallel, okay? Okay, parallel to the displacement. So if the box falls down, so the direction of the acceleration is directed towards the center of the earth, and it's also the direction where the box is falling. So hence, this is parallel to the distance or that is traveled by the object. Alright. So that force is given by gravity. So we have Fg, or the force of gravity, is equivalent to the mass of the object times the acceleration due to gravity, which is g. Alright, so force is equals mg. So we can substitute the value of the force here, or expression for the force, and get work is equivalent to mg times the distance covered, which in turns the height of the object away from the ground. So work here is of gravity is equivalent to mg times h. So this is actually equal to the potential energy of the object. Alright, so there are examples of potential energy, and we're gonna go back to this calculation later on. And right now I'm gonna give you some example of potential energy. So a woman has his stuff and he raised it, therefore it gains more potential energy as he raised it more and more. And we are all familiar with the TNT, or the explosive. All right, so it has a lot of stored chemical energy in it, and this is unleashed when chemical reaction is triggered. All right, we have a bow and arrow, and we know that it has an elastic potential energy. So the kid is trying to stretch it, and if he tries to fire the arrow, the potential energy or the elastic potential energy is converted into kinetic energy because the arrow is now moving. We have rubber band here which is stretched, so therefore it has elastic potential energy. We have a chemical energy stored in a battery that will be turned into electrical energy once a closed circuit is um, made. All right. So another familiar example is the one that I've shown you earlier, which is a bus on top of a hill has potential energy, and once it rolls down, it will be converted into kinetic energy. Okay, so let's go ahead and go back to the mathematical description of work, which is work is equivalent to force parallel times the displacement covered. So I have shown you that if you have a building and something is on top of it, so that building or that object gains some potential energy. And I'm gonna go back here and redraw it for a while. So you have the land here, which is not so flat, and you have an object right there, and it has a height. All right, let's connect this, and there's an object right there. So if the object falls down, it is caused by the interaction of gravity, and gravity is doing work on the object. All right. So it has a mass which is given, and we say that that was 5 kilograms. All right, and the height is equivalent to 10 meters. 5 kg, and we have assumed that g is equivalent to 10 meter per second squared. So we're gonna use this value to try to calculate the amount of work done by gravity in this context. All right, so work done by gravity is also equivalent to the potential energy, all right, of the object. So that is the work energy theorem. So we equate this to the force parallel that causes the motion, all right, times the distance or the displacement covered by the object. All right, so this is work, it's not weight. All right, so the force is equivalent to mass times acceleration, all right, and then multiply it by the multiply it, I just need a dot, times the displacement or the distance from the ground. All right, so the value of A is equivalent to G, so we're gonna M times G times D, and D is equivalent to the height, so this is mgh as I have shown you earlier. So this is equivalent to the work done by gravity and also equivalent to the potential energy of the object on top. All right, so on top we can calculate that. So PE now is equivalent to the mass of the object, which is 5 kilograms, all right, times the acceleration due to gravity, which is 10 meter per second squared. This is assumed and rounded off for simplicity of our calculation. We have the height of the object from the ground, which is 10 meters. All right, so when you solve this, you're gonna find out that this is 500. The unit is kilogram meter squared second squared, and that's gonna be 500 joules. All right. So the potential energy of this box right here is equivalent to 500 joules. It will then be converted into kinetic energy if it falls down. All right, so let's assume that it falls down and it's in one half. It's in a state wherein there's only it's at a height that is one half of the original height or original distance from the ground. So we can try to calculate the potential energy at that place, and we can also try to show later that it's getting converted into um, the kinetic energy. All right, so let's go and try to calculate the potential energy when the object is at one half of its height from the ground. All right, so that's gonna be mgh. So that's gonna be 5 kilograms. All right, times the acceleration due to gravity does not change, meter per second squared, it's 10. And then only the height changes. From 10, it became 5 meters. And you will see that this is 250 joules. All right, so it's just one half. So where did some of the energy go? If we say that the total energy of our system is constant. So you will see that from 500, 500 here, it went down to 250 because some of the energy is converted into kinetic energy, and we're gonna find out the formula for the kinetic energy. All right, so right now our calculation is not complete, okay, and we'll try to complete that in a moment. So here are some example of kinetic energy. So a ball that is thrown by a pitcher has a kinetic energy. A meteor that is falling from the sky has kinetic energy. Atoms that are vibrating right now have kinetic energy. A falling man has its kinetic energy. A walking girl has kinetic energy, and everything that is moving will always get kinetic energy. All right. So this is because of the body's virtue of motion or state of motion. That means if you are moving faster, that means you have more kinetic energy. All right. So even the atoms, as I have said, have kinetic energy. So if they are, if you increase the temperature, technically, they will gain more kinetic energy. So there is actually a theory about that, which is called the kinetic molecular theory, or KMT. All right, so I also have one video for that, and I'll try to do it in this channel. So kinetic molecular theorem, and be sure to click the subscribe button and the notification bell so that when it's out, you'll be notified. All right, so yeah. So moving forward, so as I've mentioned, these moving gas molecules have kinetic energy. So in deriving the formula for the kinetic energy, we stay with our premise, which is energy is the ability to do work. All right, so let's not forget that, because it will save you. It will save your grade in the near future. All right, so don't forget that. So that's the key concept in understanding the work energy theorem. Work is force times distance, and that's gonna be work is equivalent to force times d, or ma, which is the second law of motion. So here ma is just the second law of motion, which is equivalent to the force, and dx is the infinitesimal amount or change in the distance traveled by the object. So when you say when you see dx, we are entering a little and making it or approaching it using calculus. All right, so this is from calculus. Okay, so guys, since it is physics, you always have to expect that there are mathematics embedded in it, and yeah, mathematics can be simple, but most of the times complex. All right. Yeah, and when you were able to mix or blend the two properly, that's the only time you can understand better mathematics and better physics. Yes. So start practicing. It's just a matter of practice. So do not complain. All right. So where dx is the infinitesimal change in the displacement of an object while in motion. So right here, ax dx is difficult to integrate. So when it comes to integration, because ax depends on the change in velocity and dx is the change in distance. So we need to do some algebraic manipulation just to get a factor that we can use to integrate properly. And because we need to sum up all the work done along the infinitesimal change in dx, we have to carry out the integration process. All right. So since we are so there is a rule, if a certain quantity is constant, it should stay outside the integrand. All right. So here we want to integrate from the final velocity to the initial velocity, and since there is a change in acceleration depends on change in velocity. All right. So this is what I am telling you right here. So acceleration is in bf. So since we do not know the final velocity at this point in time, or the initial velocity rather, and dx is not technically not velocity, we cannot substitute the value of the variable here. So that means we need a variable that depends on x, not velocity. So that's the only problem. Okay? So we need to choose and rewrite the formula in a form wherein we can integrate using x sub 1 and x sub 2. All right. So I know that's a little bit difficult if you do not practice the calculus, or if you do not have any idea at all. Anyway, I have two ways of solving this. Okay, one is calculus, the other one is a lot easier, and I'm gonna introduce that to you later on. All right, since we want dx, we need the integration variable to be x, but since we cannot do that readily, we need a factor for ax. Yep. So yeah, to make the integration possible, we need a factor relating velocity and displacement, and we need to rewrite acceleration like this. All right. So this form tells you that there is a change in velocity in the x-axis, and if there is a change in velocity in the x-axis, that means there is an acceleration. Okay, change in velocity equals acceleration. So meaning to say, we can substitute this in our integrand and start integrating. All right, so let's do that. Yep. So from this integrand, we can now go back to dx. All right. So we can say that the movement or the work done or the change in the amount of energy is equivalent to the amount of work done, is equivalent to the kinetic energy, is equivalent to so the answer in this integrand, so it's actually 1/2 mv squared. All right, so how is it done? All right, so actually the exponent right here is 1. Okay, and add 1, so that's gonna be 2, so the new exponent will be 2, and divided by the divide that, so the sum of the new exponent will be your denominator. All right, so you're gonna have 1/2 mv squared. All right, so guys, this is a basic integration process. So when you go to grade 11 and 12, I think you are ready enough. All right. So the formula for the kinetic energy is 1 half mv squared. So you now have to integrate from B2 to B1. So the formula will be, okay, the change in kinetic energy is equivalent to 1 half mv squared final minus 1 half mv squared initial. All right. So if you're not convinced with that explanation or in that derivation, and you are more inclined to physics rather than to mathematics, I still have another formula or way of derivation for you. All right. So let's talk about that in this slide. So we'll start with work is equivalent to force times displacement, or yep. So this is actually equal to MAD, where M is the mass and A is the acceleration and D is the distance traveled. All right. So this is actually the second law of motion. Yep, as I am always telling you, that is equivalent to F. So let's move forward. And here, we're gonna use the kinematic equation. Vf squared is equivalent to Vi squared plus 2AD. So here, you see that AD, or the acceleration times displacement, is a factor. And we just have to derive it from here. So you'll see that that's gonna be Vf final minus Vi final, Vi initial velocity squared is equivalent to 2AD. Alright, so we divide both sides by 2. Alright, divide by 2. Okay, that will cancel out. So you have a formula for AD, and then we're gonna substitute that going back to our main equation. Alright, so let's go and do that, and we can write AD like this. And so you're gonna multiply it by mass and you have your new formula. So work is equivalent to, or the amount, the change in kinetic energy is equivalent to this, and that's gonna be 1 half mv squared. All right. So Ke, or the Pe, or potential energy plus Ke, is equivalent to the total energy of the system all throughout the process, and that is constant. That is the basic formulation of the conservation of energy. And we can actually use the formula that we just have derived to show the relationship. Alright, so I hope you guys learned something about it. So in the next video, we'll be talking more about the conversion of several types or several forms of energy. And God bless, guys. Thank you for watching, and thank you for tuning in. I hope you learn a lot and will be able to pass all of your exams. Bye bye, guys. See you next time.